Okay. So this is the problem that we skipped yesterday. We didn't have enough time. You answered the question below it. And all this question asks is find A and B so that F is differentiable everywhere. Now I've thrown this word differentiable out over and over and over again. Anybody want to take a gander to what differentiable might mean? Yeah, it means there's a derivative anywhere on this function, right? Cool. So I got something differentiable. So how am I going to find A and B to make it differentiable everywhere? Why? Why do you think that? Because I haven't said anything about it. I just said that it's differentiable, so you're kind of adding an extra thing to it. So I'm just curious what your logic is. And okay, you know, that's kind of the cool part about this class. You can be logical, and if it works, awesome. And if it doesn't, well, dang. So you're asking me, does it have to be continuous? Why? Okay, so you're saying if there's a point that's missing, you keep your mouth shut, Armando. Jerk. So you're saying that your logic is if there's not a point there, how can I have an actual derivative? Because what is a derivative? Slope of a tangent line. So you're basically saying because there's no point there, there's no way I can make a slope that's tangent at that point, because we would be missing that whole tangent concept. Oz is like, you know what? I'm going to buy it. I like that. We're going to go with that. What do y'all think? Maybe, maybe not. You think that works? It doesn't work? They're not my words. I'm going to say these are Jake's words. So if they're wrong, then everybody blame him. And if he's right, I was clearly leading him in that direction, and I get all the points. It's not how it works at all. So Jake, you're all in on this, eh? You're thinking continuity is important. Well, let's do some continuity work. If continuity is important, and if we have to, we can cross it off. If continuity is important, what do we have to show for that? Hold on. I'm gonna pick on somebody. I gotta practice this. I'm not good at this picking on people thing. Oz, what do you think? All right. Oz's question has been thoroughly answered. What do you think, Abel? Continuity. What do I have to show?
Limit and the point are equal.
The limit and the point are equal. Well, you're kind of making a couple of assumptions there. What assumptions have you already made?
The limit and the point exist.
Yeah. All right. Now realize I wanted to be kind of picky. Had to pick on you after you said it. Abel's statement was that the point and the limit must be equal to each other, but of course we can't make that statement until we've proven that the point exists and the limit exists. So the point, f of what, because where could this be discontinuous at? 2. So you're telling me the f of 2, that's going to equal what? What do you think, Shiv? What is the f of 2? I'm on Shiv. Picking on Shiv now. Yes, you do. When do we equal 2? Does it equal 2 on the top line or the bottom line? Okay. What is the x? Now put it all together. Yeah. So? I don't care about that. Oh. Psh. Get there when we get there. So, there we go. That explains why Shiv was going, I don't know how to do it. I'm not sure how to get that without knowing A. Cool, see? You're worrying too much. So we have to show that a point exists, and then Abel said we have to show that a limit exists. All right. Ooh. All right, Armando. How do I show that the limit exists? It's like old school. You haven't done this in like a year. I know. Yeah, what do we have to prove for a limit to exist? I know this is something that we talked about a long time ago, so I'm just trying to make sure we're on the same page. Need some help? Pick somebody. For a limit to exist, that means what has to be true about the limit at 2? There it is. Edwin, help me out. Never mind, I have the answer. Way to go. We know that the limit as x approaches 2 from the left and from the right of f of x in both cases have to equal the same thing. So from the left side and from the right side, what is that, 2b minus 3? And for the limit to exist, we need 4a plus 1 to equal 2b minus 3. Well, I've already seen the 4a plus 1, so that's good. So when these are equal, the point and the limit will equal the same thing, and we will be good to go. But I got a problem. And it's not that I sneezed. What is my problem? I got 2 variables. How do I find the 2 variables if I've only got one equation? What am I substituting? No, not that. You cannot. Please do not put your shit in my problem.
You recorded that.
I did. But you're the one who said poop. But if I solve for A and plug it in for B, then I'm just going to get the whole thing canceling each other out. What do you think, Astrid? I can't really factor anything at this stage. I want to go back to where we started off. Nina, what did you say about differentiability? Derivative has to exist everywhere, right? So what? Basically. This is where we enjoy the whole fact that we play calculus. You got to play some calculus popcorn on occasion and just throw ideas out there, right? If it's differentiable, then what I'm also implying is that when I take f prime of x, which in this case is going to be what, 2ax and b. Now, I'm going to do something here that's really important. What do you notice I didn't put there? Okay, 2 reasons why that's important. Number 1, if that's equal to, if I put an equal to there, what am I telling you? I'm telling you the derivative exists, which is not necessarily true yet. We don't know if it exists, so I can't put it there. The other reason why I want to deal with that is, remember when we talked about the definition of a derivative, what is the important part of a definition of derivative? What does the definition of a derivative have in it? It's on your 3rd sheet of paper? Or no, it's on the 2nd sheet of paper, front of the 2nd sheet of paper of your packet. Yep. has a limit. So a derivative by nature is and for a limit to exist, what did you say, Armando, earlier when we talked about the limits? Yeah, left side has to equal to right side. So what I need to do is I need to look at the left side limit, which would be, in this case, 4a needs to equal the right side b. And if those equal, then we'll know if the derivative will exist at 2. It's okay. No, seriously, please double check my work. Running through your head, going, does that make sense? Yes, it does. Okay. Well, and further down the road, it's really nice that I have, 30-something odd, 40-something odd people who basically double check all my work as I go through. No. Well then, can you at least promise that if you make the assumption that you're wrong, you ask me why you got a different answer that's clearly wrong, so that when I've screwed up and you've done it right, we can correct my mistake by assuming yours was, we're going to follow the if mine's wrong, then yours must be right concept. So solve this. Figure out what this is going to be. You've got A and B. You can do this. This isn't crazy. This is good stuff. Solve for A, solve for B. Come up with an answer. We're setting them equal to each other at 2. And we're trying to figure out if we're trying to set them equal to each other. So if you wanted to put an extra line in there, what we're doing is the limit as x approaches 2 of f prime of x from the left is equal to the limit as x approaches 2 from the right side of f prime of x. We're checking the limit concept of it first, and if that exists, maybe that'll come up with something. Has anybody got an answer for that yet? You have A? What is A? Excellent. That means B has to be what? Has to be 4. I got a real quick question. How many people solved this question? How many people did this? How many of you did that one? Okay. Did anybody by chance do this one? That's a whole lot easier, isn't it? Well, he did substitute, but how many people substituted the B in for 4A? Nicely done, Oz. Huh? Did you get 4? Yeah, did you get 4? If you did, then you got it right. A is 1, B is 4. The reason why I like this particular question is partly because I love to watch students' faces when they realize that I didn't sub out for just a single variable. I just replaced the whole doggone 4A. You can do that, for those of you that didn't know. This class is not nearly as amused. Last period thought it was the coolest thing ever. Pretty sure someone almost threw a shoe at me.
So, there's like a discontinuity or something. You can't have it derivative.
Okay. You are 100% correct. And I do want to take a moment to go back and talk about that, because what I find interesting is usually discontinuity is completely ignored in this type of question, and I have to point people back. So the fact that you're already thinking about the concept of continuity and how that will attach into differentiability is a huge first step. Yes, that is absolutely 100% true, which leads us to the next day's notes. Differentiability. We are actually going to formalize differentiability. Oh, goodness gracious, I need to smart view. All right, well, I'm bringing up this. So, what is differentiability? Differentiability is looking at different points along the graph. Just like continuity, how I'm looking at specific points, differentiability is looking at each and every individual point on a curve and deciding if the derivative can exist on that curve at that point. Okay? So when I talk about differentiability, and something that I didn't mention right at the beginning with fifth period, and then some people ask questions, is that what I'm going to do is I'm looking for a specific spot on a graph that would cause a function to not have a derivative. All right? One of the major reasons is that a function has to be continuous for the derivative to exist. Because if there is no point there, you can't have a tangent line. Because by definition, the tangent line has to touch at that point. So that was exactly where I wanted you to be. Now I do want to point out right here, this one where we're talking about this type of discontinuity. This is an asymptote. Remember, as you go through math, don't be an asymptote. Yeah, it's good stuff. So this is an asymptote. Remember that there are two other types of discontinuities. There are jump discontinuities, and you can also have a point. And that one is also known as a removable discontinuity. All three of those instances would all warrant a function not being differentiable at the discontinuity. So this function right here that we're looking at is discontinuous only at x equals 2. Everywhere else on that graph, this is differentiable. That is okay. It's a single location. And what you're going to find out is that it's much easier to define when a graph is not differentiable and say it's differentiable for everything else versus the reverse of that. It's because you think you'd have to check every single individual point. Well, how are you going to do that? It's a very, very difficult check. So what I wanted to show you here is an example of the next concept here. The other thing I mentioned is this concept of local linearity. All right? Hold on, I don't want to use that function right away. I'm going to take a function that is differentiable. All right? X squared is going to be differentiable, in case anybody's curious. And we'll go ahead and we'll graph it. I just want the x squared right now. All right. Whoops. That's not what I wanted at all. Trace when x is 1. All right. We're going to come over here. At that spot, is that a line? Definitely not. Watch what happens when I zoom in. As I zoom in on that point, that definitely is not a line. Let me zoom in more. Ooh, that's kind of curved. Just a little bit, not much. Hold on, I have an idea. Let me zoom in. Oh snap, what's that starting to look like? That looks a lot like a line to me, doesn't it? Zoom in one more time. Yeah, now we're getting all sorts of crazy up in here. There's no way. You cheated. Actually, I did cheat. Use the idea of a limit. The idea of local linearity is as I approach this particular function, essentially what am I doing? I'm taking those x values and I'm just bringing those x values closer and closer and closer to my point, right? Also known as taking a. And as I take that limit, I'm saying, okay, let's turn this into a line. That's going to be this idea of local linearity. Now let me juxtapose that with this example. I need to zoom into a regular. This is an example of a function that is not differentiable, and here's why. Let's go trace 3. That looks good. Zoom in right about there. All right. Does that look like a single line? Definitely not. Well, okay. Last time I had to zoom in like 3 times, right? Well, that's kind of weird. Folks, what's the problem? What's happening? I can't argue that at all. What's happening? It's an upside down pyramid. If I keep zooming in, it doesn't matter how far I zoom into this function. Will it ever look as if it's a line? Why not? Well, what can you tell me about the slope coming from the left side? What type of slope is it? Can you tell me about the slope on the right side? So if we think about a limit or a derivative as a limit, as we approach from the left side limit, when we think about the slopes, doesn't equal the right side limit of the slopes. Therefore, the limit does not exist. So there are 2 types of situations where we're going to deal with local linearity. There are going to be situations that have a sharp turn, not necessarily always an absolute value function. A sharp turn could be, yes? The limit of the derivative does not exist at that point. So a derivative talks about what? Slopes of a tangent line. So if you think, we talk about the limit of the derivative, this is always going to be -1, agreed? So as I get closer and closer, the slope of this line is always going to be -1, agreed? If I take the limit of the derivative coming from this side, the slope is always 1. So this is -1. This is still -1. This is still +1. This is still -1. Still +1. But at 2, when I have a negative and a positive, does that limit actually exist? Of the slopes. So, if we think about what the graph of the slopes would look like here, the slope of the graph here would always be -1. Agreed? And then at 2, something's going to happen, because at 2, the slope becomes. So if we think about the derivative function, the limit of the derivative function, which is the slopes, does the limit at 2 exist? Because the left side and the right side have different angles coming in. That better? Aha, visual. I'm comparing the slopes for differentiability in this case. So what this is saying is that the limit as x approaches, in this case 2, of the f prime of x does not equal the limit as x approaches 2 from the left and from the right, of f prime of x. That's what we're saying. And if you notice, that's going to be the same exact argument for question number 4. Because the left side limit is going to be what type of a number of the slope? A negative. And the right side limit of the slope is going to be a positive. So again, we still have the limit as x approaches 1 from the negative side of f prime of x is not equal to the limit as x approaches 1 from the right side of f prime of x. Let me make sure I did put not. So a cusp and a sharp turn, do you have to know which one's which? No. Apparently, on the AP test, they even let you use either word interchangeably, even though mathematically that's not correct. Huh? Cusp and sharp turn. Technically, a cusp, by definition, the slope goes to infinity, negative infinity or infinity. And in a sharp turn, the slopes go to finite values. Yeah, they apparently don't worry about that. Apparently, you can also call those kinks in the graph, according to the chief grader, but you can't call them doink points. That was literally written on the explanation of things you can't put as an answer. There were enough students that they said a doink point does not count. the only thing I can think is that there's a teacher who goes, all right, so you follow the curve, and then suddenly, doink, there's a, and so they called them doink points. No, we will never call them doink points because I don't want to be the teacher who does that. Okay, so anybody watching this video, there are no. There we go. I'm gonna freak them out again. There are no doink points. Never put a doink point. Wouldn't be the first time. They said 26 minutes of silence. I'm really hoping that's not the case. All right. The last but certainly not least is here at 1. We have a vertical tangent line. Yeah, there are. Click. Oh, no. All right. Vertical tangent lines. At x equals 1, there is a vertical tangent line to this graph. Why is that considered non-differentiable? It's not a zero slope. There we go. I know, I'm picky about that. All math teachers are picky about that. This is an undefined slope. So by definition, if the slope is already undefined, then how the heck did a derivative exist there? Realize what I'm talking about here is we're talking about all of these ideas of at that particular point, the slope does not exist. We're talking about the slope from the left and right don't agree, or there's no point at all. Also, one more thing. You will sometimes get questions that will say, given that a function f of x is differentiable, prove blah, blah, blah. As soon as that happens, if you're trying to prove anything, somewhere on the paper you need to write, since f of x is differentiable, it is also continuous. Differentiability will always mean that the function is also continuous. However, if I tell you the function is continuous, well, is 4 continuous? Sure. Is it differentiable at 2 or at 1? No. Is the graph of 3 continuous? Sure. Is it differentiable at 1? No. So continuity does not imply differentiability. It only works the other way around. Yes?
Is that extra board? Is that you said cusp?
Yeah, if you actually, the intention here is that as we approach the 1, for posterity's sake, the actual answer to this is 2/3 x minus 1 to the 1/3 in the denominator. That's what the f prime would be. We're going to learn how to do that later with a more complicated function like that. So when x is equal to 1, this goes to 0, and as x goes to 0, this goes to negative infinity. Agreed? But what winds up happening is we approach from the left side, this goes to 0 from the as a negative, or this goes to negative infinity, and as we come from the right, it goes positive infinity. And that's kind of the issue that we run into, is that they're negative infinity and positive infinity coming in at the same spot, so we get a weird cusp. Again, I would not worry too much about that definition. That is the mathematical definition of cusp. If you meant cusp but you put sharp turn, or you meant sharp turn and you put cusp, they're not holding you accountable to that extreme of a level. There's enough other things to memorize in this class. Knowing the difference between a cusp and a sharp turn is not one of them. All right, which is why I teach it to you as a limit approach method anyways, because if you say the left limit and the right limit are not equal, you don't have to say cusp or sharp turn, because you've already shown me the derivatives limits aren't going to match. All right, so I've given you 2 graphs. Each graph has the same exact A and B question. Question A, identify all points where the function is non-continuous. So looking at graph 1, I don't want to pick on. I want to pick on cat right now. When is question 1 not continuous? Why? Take a shot. What would you say? Remember, keep it simple. What's there? What is it? Beautiful. There's an asymptote there. You're right. An asymptote. Good old asymptotes. All right. Andy 1. Okay, you're first on the, so you're officially Andy 1 because of seniority on the last name list. Sorry, Andy 2. Are there any other continuity issues on question number 1? Is there any other spot where there's a discontinuity? Okay. Where's there a non-differentiable location? If one, of course, exists. Bum, bum, bum. Yeah. Now, what is your reasoning here? Oh, man, that's too much work. I'm just going to say not continuous. If it's not continuous there, we're done. Too much work. Don't think hard. You don't want to think hard. All right. Trend. Got a second graph there. Are there any discontinuities? Remember, you're looking for a discontinuity. This is a continuous function. Woohoo! Now, since you already started saying numbers, I'm gonna have to pick on you now. Where are the non-differentiable spots? And why would you say? Pick one of those 4. So, yeah, well, and these I would actually probably call them sharp turns. Or you can say cusp. Those are going to be interchangeable in this course. Or my preferred thing, I would probably say something along the lines of the limit as x approaches -3 and +3. I don't know how I'm going to actually write this together. Sure, from the plus side and the negative. You know what, we're going to write this. Left limit not equal to right limit. There we go. That looks good. Sure. Did I just tell you what's happening? Part of the reason is I really just didn't want to write. I was trying to find a way to combine the limit notation for -3 and +3, and it wasn't working. I would have had to have written 4 limit statements then, and that's just goofy. I don't feel like that. Jake, what do you think? That seems goofy. You're thinking. Change the direction? Yeah. No, you're right. Anywhere where there's a sudden change of direction would be a location on a graph where we would find discontinuity. Or not, but non-differentiability. Yes? No. Good question. So it could also be something that looks like that, right? In this case, there is still a sharp turn. It's a positive slope to a positive slope, but there is a sudden change of direction, okay? So it could also, and that's where things get hard because sometimes you get things where like it's a curve, but then it comes straight out. But at that spot, they equal the same thing. So that would technically be differentiable. So you have to check the left side versus the right side. In a graphing situation, I am going to make it obvious. On your test, you are going to get a question similar to 1 and 2, where it's going to be identify all the locations where there's a non-differentiability, where it's non-differentiable. I'm going to say be careful of that. Don't just look for sharp turns and don't just look for discontinuities, but also pay attention to the fact that there could be vertical tangent lines as well. And if there is going to be a vertical tangent line, I've probably given you a descriptor to imply that it happens. I don't want to go too much further into that question. All right? Know that it's coming and make sure that you're critical of it and that you think everything through that I've said in that problem. Nice. Yes, what do you want, Armando? No. Okay, what do you really want?
So we put x equals plus or minus 3, that's wrong.
If you put x equals plus or minus 3 and then you, yeah, if you write plus minus 3, that's perfectly acceptable. That's reasonable. I don't know why I wrote it in a set notation this time. Typically, I'm lazy and write plus and minus 3 too, so I had to screw with things. No, that's good, and always double check notation. Sometimes I'll catch something, sometimes I won't. Sometimes I'll write things different just for the sake of writing things different, just to mess with you all. Actually, it's not to mess with you all. Hold on, let me tell you. It's not to mess with you all. It's to expose you to different forms of notation. Yes, that's what I'm saying. All right. So when dealing with continuity and differentiability of piecewise functions, you've got a couple things you have to check. We need to examine the x value of the rule change. We need to make sure it's continuous, and then we have to show that the left derivative is equal to the right derivative. You can see that notation officially in text right there. I've been putting it on the paper in several other locations, but that's what I want you to check. So for instance, if I say determine if f of x is continuous and or differentiable at the value of the function where the rule changes, all I have to do is show is it find if the continuity works and then show that the left and right derivatives work. Don't do differentiability first, because if I take the derivative and it works, but then at that point it's not, could I have a graph that comes up and looks like this, and then a graph that does this? Would the derivative still be equal? Sure. Look, that looks like it goes to 0, and this looks like it goes to 0. The slopes look like the slopes are both 0, right? But what exists here? A discontinuity, right? So if I go and I show that it's continuous first, I don't even have to worry about doing a derivative. So how do we show continuity? Okay, does the point exist? Does f of 2 exist? Minus 12? Is it 2? Do you agree? 4 plus 10 is 14 minus 12 is 2? I think. Wouldn't be the first time I screw that up. All right, let's check the limit as x approaches 2 from the left of f of x. What is that going to be? Well, hey, guess what? Oh, no, that's a different equation. That's one thing to also be careful for, and I think most of you have done a good job of focusing on that. Pay attention to which one's left and right. The top is not always your left limit. So the left limit is 4 minus x, which is 2, and the right limit is 2. So f of 2 equals the limit as x approaches 2, which is definitely 2. Boom. Are we continuous? Check. So for the derivative, what do we need to do? For differentiability, we have to find f prime of x. What is f prime of x? And? And am I going to include the equal to here? Nope, I'm going to ignore that because I don't want to force it to be that. So let's check the limit as x approaches 2 from the left of f prime of x. What is that going to be? So whoops. It's just -1. There's no x's. That made life easy. And we not the limit as x approaches 2 from the right side of f prime of x. -2. -1 is not equal to -2, therefore it's non-differentiable at x equals 2. And you are done with the problem. did it. We did a differentiability problem. So try the multiple choice question. Cool. You got plenty of time, I think. I don't know. I erased my schedule. Leave it 35? Well, you got 1 minute. I will tell you, I'm not going to give a homework assignment attached to this today. What I want you to do is when you get home, you have a review. I'm not making the review a requirement. Reviews are for you. However, last time I've checked, any time I've ever given a review, that's pretty much the one thing I'm guaranteed to get everybody to do. Answer key is available on Schoology. Feel free to, my suggestion, get it done today. I gave you the answer key today so that if you have problems, tomorrow you can ask. Groovy.